session, the last class, but it's been some weeks after we talk about this. So uh, I want to review a little bit. Let me review the first part of the these chapters. Now, what is the definition of the multiple linear regression model? Okay. Now, if we look at this equation, we have more than one exponential variable. So when we have more than one exponential variable, we say multiple regression model as opposed to the simple regression model where there is only one exponential variable. Okay, so let's define variable. The y on the left side of equation we call dependent variable or explained variable. And we have the x variable on the right side of the equation, and that variable we call independent variable or exponential variable. And as you see, we have more than excuse me, more than one exponential variable, so that we call multiple regression model. Okay. In addition to this dependent variable and independent variable, we have the error term denoted by little u, and this represents unobservable. The factor which are not observed in the market, but the factor which affect the y. Okay, so all factor other than these x variables are contained in the error term. Okay, then we have the parameter beta parameter, and we have beta naught, beta 1, beta 2, and so on. And beta naught we call intercept, and the beta 1 and beta 2 and beta k we call slope parameter of the respective exponential variable. Okay. Now, why we do multiple regression? Okay. What are good about multiple regression? There are three good things about multiple regression. The first thing is we incorporate more exponential factors into the model, so we expect we should be able to explain better. We should be explain better the variation in y by incorporating a more exponential variable. Okay. Second good thing is by having multiple regression, we can explicitly hold fixed other factor. These other factors that otherwise would be in error term, but in this case, we can take out these other factors from the error term, and once the factors are taken out from the error term, then we can explicitly hold those factor fixed. Okay. If they would be in error term, then we cannot hold those factors fixed. Okay. So by having a multiple regression, in other words, by having taking out factor in from the other factor, we can explicitly hold those factors are fixed. Okay, so that's the good thing about multiple regression. Okay, this second thing I will talk about more later on. The last good thing about multiple regression is the multiple regression allow for more flexible functional form. Okay, so I will give example later. Okay, so let's take an example of the wage equation where we have two exploratory variable where the first variable is the years of education. Second variable is the labor market experience. Okay, so these two variables are supposed to explain the variation in hourly wage rate of workers. Okay, now if suppose that we estimate the beta 1, this is the slope parameter of education, then this beta 1 measure effects of education while holding the other factor experience the fixed. Okay, so that's the good thing about the multiple regression. Okay, when you run the multiple regression and you estimate the slope parameter, and that means that measure effect of the only education and holding the other factor constant. Okay, so let's take a look at the another example which have the average score. This is the average standardized test score of school will depend on first per student spending at this school and average family income of student at this school. Okay, and little u contain the all other factor. Okay, okay, now suppose that first of all we notice that the first student spending, the first exponential variable, and the second variable, which is average family income, is likely to move together, to be correlate at a given high school because of school funding, financing. Okay, so if school has the greater funding, then the average, the average family income higher and the student spending will be higher. Okay, so it move together. Okay, so this is the case where first variable and the second variable move together, correlate. Now suppose that, so this is the multiple regression, but instead of running multiple regression, suppose that we run the simple regression by omitting the second variable, omitting the average family income in regression. Okay, in that case, the second variable would be contained in the error term. Okay, in that case, you estimate the effects of per student spending on average score, and you don't have a average family income variable in the regression. Okay, in that case, in other words, when you omit average family income in your regression, you will have a bias estimate of the effect of spending on average test score. Okay, so what it means is that you omit the average family income in your regression and you estimate the beta one. In other words, the simple regression. Then that estimate will be a biased estimate of the effect of spending on average test score. Okay. In other words, when you omit the average family income in your regression, like in a simple regression model, average score regress only one variable expenditure. You don't have average family income. In that case, you estimate the slope parameter of spending, then that slope parameter estimate that effect of per student spending could partly include the effect of family income on test score. Okay, so let me repeat again. Suppose that you omit average income in your regression, so you run a simple regression. Okay, and you estimate the beta one, the slope parameter of the expenditure, and that you estimate will also not only include the effect of spending, but also the effect of average income, which is contained in the error term. So that means that your estimate of beta one in simple regression will be a bias, because when the expenditure higher and at the same time the average family income will be higher, and so the average test will go up because not only spending go up but also the average income higher. But in a simple regression, the average income, you omit this average income variable, so you only estimate the effects of spending, and that estimate bias will overestimate the effects of spending on average score because it includes partly the effects of average income, which is contained in the error term in a simple regression. Okay, so what's good about the multiple regression? Now suppose that you take out the average income from the error term, so you have two variables and you estimate the beta one, and this beta one measure the effects of expenditure while holding average income fixed, so you can avoid this biased estimate. Okay, so that is the very good thing about the multiple regression. You can more likely avoid the problem of bias estimation. Okay, now the good thing about the multiple regression is it allows more flexible functional form. We have said that the good thing about that is that the multiple regression allow for more flexible functional form. Okay, so let's look at the example to show that. Okay, so look at this example. In here, we regress family consumption on income. Okay, but you can have the another variable, which is the squared income. When you have the simple regression, you can only regress consumption on income. But when you have the multiple regression, you can have the more another variable, in this case, the squared income. By having squared income in your regression, where it's a multiple regression, you have this is the more flexible functional form. Actually, this is the quadratic function, okay? So by having multiple regression, you can have the squared income term as the another explanatory variable. And by having another squared income variable in your regression, your model become more flexible. It allows for quadratic function, okay? So when you have this quadratic function in your model, what's the benefit is that, I'm sorry about that. By having this quadratic function, what is the benefit? Okay, so in this case, so you suppose that you take the partial derivative of consumption with respect to income. Okay, so you take the partial derivative of consumption with respect to income, then that will be this term will be beta 1, and the derivative of the second term will be 2 beta 2 income, okay? So this partial derivative measure how much consumption change if income increase by 1 unit. Okay, so how much consumption change when income increase by 1 unit? That's what we call in economics, we call marginal propensity to consume. And this marginal propensity to consume depends on, you see, the level of income, okay? So you may compare this marginal propensity to consume between lower income family and the higher income family. Suppose that the income increased by 100 for both lower income family and the high income family. Then the low income family tend to spend more out of 100, maybe out of, if income increase 100, then consumption increase maybe 90, something like that. But for higher income family, when income increase by 100, consumption increase maybe 60, okay? So how much consumption increase depends upon the level of the income. It's different between the low income family and the high income family, okay? And that is the empirical fact. So by allowing for this more flexible functional form, in this case the quadratic function, we can capture that the difference in marginal propensity to consume between the lower income family and the higher income family, okay? Because you see that this marginal propensity to consume, which is the partial derivative of consumption with respect to income, depends on income. If you do not have the second term, then this partial derivative will be only beta 1. In that case, the marginal propensity to consume same between lower income family and the higher income family. But when you have the quadratic function, we can differentiate the marginal propensity consumed between lower income family and the higher income family. So this quadratic consumption function make more sense. And so you can, by having a multiple regression, you can allow for this the quadratic function, more flexible functional form. Okay, so that's the good thing. That's the good thing about the multiple regression. Okay. Okay, and this is the similar example. So let me skip that. Okay, let me skip. So we define the multiple regression model, and we talk about what are the good things about the multiple regression model. Okay, now how we can estimate the multiple regression model. In other words, how we estimate the parameter, slope parameter, and the intercept and slope parameter. How we can estimate. Okay. One way to estimate is we use that the OLS methodology we call ordinary least square method. Okay, let me actually we talk about this ordinary least square OLS ordinary least square method when we talk about the simple regression model. Okay, and it's very similar for the multiple regression model. Okay, so first we have the random sample. Okay, so here I from 1 to n. So we have the n different family. Okay, we have a n independent family. Okay, and for each family, for example, we have the observation. Maybe this is the maybe walk, for example. Okay, and independent worker. Okay, so this is the ways. Okay, so suppose that we have the sample of n worker and independent worker. Okay, then we have the observation. For example, x1 could be years of education, and x2 is a job experience, and so on each workers, and the yi is the wage rate of each worker. Okay, so you have a sample of n independent workers, and you collect the data on this uh, years of education and job experience and wage rate and so on. All right, then suppose that you run the regression and estimate the parameter. Here you have the parameter. On top of that, you have the hat. Okay, so this is the beta not hat, and this is the beta 1 hat, and this is the beta 2 hat, and so on. The parameter with hat, that is that the estimate. Okay, that is not the true value, that is the estimate value. Okay, so suppose that you run the regression and you estimate the this parameter, including intercept and the slope parameter. Okay, then from your regression, this term is that your predicted wage rate of the workers. Okay, so the term except for yi on the right hand side, that is that the predicted wage rate from the estimated regression. Okay, so yi is the actual wage rate of ICE workers, and the second, this is that the predicted wage rate of the ICE worker. So difference between actual and predicted wage we call the residual. Okay, so residual has the head on top of it. Okay, so this UI head we call regression residual. Okay, so difference between the actual wage and predicted wage. Then our job is to find the formula for beta naught and beta 1 and beta 2. Okay, so how we are going to find the formula for this parameter. We set up the optimization problem, and here we have the minimization. So this, if you look at this is the sum of squared error. So we want to minimize sum of squared residual. How? By choosing this parameter, we want to minimize the sum of squared residual. Okay, so you solve this minimization problem. With respect to this parameter, and so you solve for that, then you could find the solution for all these parameters. And this, when you have the many variable in your regression, this optimization problem quite complicated. So the your computer will carry out this minimization problem. But this is the way how we find these parameter beta naught, beta 1 hat, and so on. And if you find this parameter through this minimizing the sum of squared residual, we call that is the OLS, least square. We want to minimize the square. Okay, least square, ordinary least square. Okay. So now what this the slope parameter means. Okay, what the slope parameter means. Okay, so go back to in here. So for example, in this case, what the slope parameter means, beta 1 or beta 2. Okay, that is the partial derivative. Okay, so you know the meaning of partial derivative. When you take the partial derivative, you only allow the change in the xj while holding all other variable constant. Okay, so this beta j measure by how much dependent variable, which is y, change if j's, in this case xj, j's independent variable increase by 1 unit. Here the point is we are holding all other independent variable and the error term constant. Okay, so that's the meant by the partial derivative. Okay, so we are holding all other variable constant. Okay, so in this case, for example, you estimate the beta 1, and the beta 1 means it measure how much the salary increase when sales increase while holding all other variable constant. Okay, or this variable. Okay, in this case, what this beta 1 means, measure when how much the average score increase when the per student spending increased by 1 unit, while the other variable, average family income, fixed. Okay, so that's what it meant by the partial derivative. Okay. Okay. So by having multiple linear regression, we could manage to hold the value of other variable fixed. Okay, so that is the second good thing about the multiple regression. Okay, we can hold all other variables fixed. You estimate the multiple regression, and then this your estimate that measure how much y change when the x variable change while holding all other variable constant. So by having multiple regression model, we can hold the value of other variable fixed. Okay, so that's the good thing. That's the good thing about the multiple regression. Okay. So here is the example in here. So here we have the college GPA. Okay, so this is the estimate. Okay, estimate regression model. Okay, so here we have the grade point average at college. Okay, and your estimate is the intercept 1.29, and your estimate of the slope parameter is the 0.453 associated with the high school GPA, and this second slope, you estimate the value of this second variable is the 0.0094, which associate with the achievement test score. So what we're saying is your college GPA depends on your high school GPA and also your achievement test score. Presumably, if you had a good high school GPA, we expect that your college GPA will be higher. In other words, if you are a very good student at high school, then you more likely that you will be a good student at college too. And also, if your average achievement test score is high, you had high achievement test score, then we expect that you will do well. You will have a good job at college. Okay, so that's what this regression model is supposed to predict. Excuse me. So in here, so if you have another point on high school grade point average, holding average, holding achievement test score fixed. Another point on high school grade GPA associated with another 0.453 points college GPA. That's what I mean. Okay, so what does this mean? If a student had higher high school GPA by another point, while we're holding his SAT fixed, then we predict that his college GPA will be higher by 0.453, okay? Or equivalently, if we compare two students with the same SAT, but the high school GPA of student A 1 point higher, then we predict that student A have a college GPA that is 0.453 higher than that of student B, okay? So what it says, we have a two student, A and B, and student A and B have the same SAT. So meaning we are holding this SAT constant, same. But student A high school GPA higher than the student B's high school GPA by 1 point. Then we predict that the student A college GPA will be higher by how much? By how much? 0.453 higher than that of the student B. Okay, so that's what it meant. Okay, so that's what it meant. So we only allow to change the high school GPA, but we holding SAT fixed. Then this coefficient tells you when high school GPA up by 1 unit while holding other factor fixed, how much college GPA increase. So by having another variable in your SAT variable in your multiple regression model, we can explicitly hold this fixed when you estimate this one, okay? When you estimate this, the college high school GPA, the slope parameter, we can explicitly hold. But if you do not have this SAT variable in your model, if you have a simple regression model, this would be in the error term. Then if this is in the error term, then we cannot hold SAT term fixed when you estimate this slope parameter, okay? In that case, you have the bias problem, okay? All right. So that is very good thing about the multiple regression, okay? So let's talk about more about this one. This one is the partialing out. We can have another interpretation, so-called partialing out interpretation of the multiple regression, okay? There is a second way to estimate. Second way is that we regress the exponential variable on all other variables. So in other words, we regress high school GPA on SAT, okay? Regress one exponential variable, high school GPA on SAT, okay? Then you have the residual from the first regression. Then the regress y on the residual from the first regression. Then the estimate coefficient of exponential variable in multiple regression will be the same as the estimate you done in following a two-step. Okay, why is that? You can either estimate the multiple regression model or equivalently you can estimate in two-step. I told you the two-step, then your estimate will be the same. Then you may ask why. Why the same, okay? So remember the residual from the first regression. In this case, you regress high school GPA on ACT, then the residual from the regression is the part of the explanatory variable, part of the high school GPA, which is not correlate, which uncorrelate with the other explanatory variable, which is the ACT, okay? Because the residual, that's the residual, so that is the part of the high school GPA, which is not correlate with the ACT, okay? Then you regress the y on the residual, then the slope coefficient of the second regression. Second regression is regress y on the residual. Represent the separate, isolate effect of explanatory variable on the dependent variable. In other words, that represent the isolated effect of high school GPA. In other words, the effect of high school GPA, which is uncorrelate with ST, okay? So if you estimate in two steps, the result is, the slope is the isolate effect of the high school GPA, which is uncorrelate with SAT, and that is the exactly this coefficient in the multiple regression. In this case, this coefficient represent the effect of high school GPA while holding this SAT constant fixed. Okay. So that is another interpretation of this coefficient in multiple regression, okay? All right, so so much for, let's see, I will give you exercise to make sure that you understand. So just a minute. Okay. Let me see. Okay. Hello, can you see the slide? Hello? Anybody answer me? Anybody answer me? Can you see the slide? Hello? Hello? Anybody answer me? Hello? 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 Okay, let me see what I'll do. Okay, can you hear me? All right, okay, let me see. Oh, Jesus. Oh, Jesus. Jesus. Okay. Oh,
Teacher, I can hear you. You are turn up on the mic.
So can you hear me?
Yes.
Okay, let me start. Okay, sorry about that. Okay, sorry about that. I'm sorry. Oh, okay, sorry about that. Oh, let's try again. Okay, let's try again. Let's try again. Okay, so. So you can hear me, right? Okay, let me upload the slide. Okay, I think you can hear me, right? All right. Okay, let's start again. Goodness of fit, and this is a about how well your regression explain the variation in y. Okay, and we can decompose the total variation STT into the explained variation, what we call SSE, that is the variation in y explained by your regression, and SSR, that is the variation in y unexplained by regression, that is actually variation in residual. Then we have a statistic which we call R square. And R square statistic measure how well your regression explain the variation in y. And we define R square as the fraction of explained variation to total variation. So if your regression explain 100% of the variation in y, then the fraction will be 1. So that when you have the R square of 1, your regression explain 100% of the variation in y. On the other hand, the R square is 0. Your regression does not explain at all. So basically, R square lie between 0 and 1. And higher value of R square, it means your regression explain the variation in y more, better. Lower R square means your regression explain less. Okay, so other things being equal, we like to have the higher value of the R square. There is the alternative expression for R square. If you look at this formula, R square is the ratio of squared covariance between yi and y hat, and denominator the product of the variance of the y and the variance of yi hat. Okay, and this is exactly what the correlation coefficient. This is the exactly correlation coefficient between the actual yi and predicted value y hat. Okay, so R square is equal to the correlation between yi and y hat. And if this correlation is 1, then it means that the y hat perfectly move together. It means that you can predict 100%. Okay. In other words, same as the explain part, your regression explain 100%. If the correlation is 0, that means that your predicted value is independent of the actual value. It means that your regression doesn't explain variation y. So there are two expressions. But anyway, R square means how well your regression explain the variation in y. Okay. So let's take a look at the example. Okay, this is the economics of crime. So we want to explain the number of times arrested crime in 1986. And as an exponential variable, we have the proportion prior arrest that led to conviction. In other words, how many arrests are led to conviction? Conviction means you plead guilty, okay? You plead guilty in court. So the more you plead guilty, less likely to commit crime. The second variable is the months in prison. So this is how long, how many months criminal spend in prison when criminal is convicted. Okay. So longer months means that the less likely to commit crime. You have a negative sign. And the third variable is the quota employed. And this is the opportunity cost for criminal. If criminal can find other opportunity, other job, then criminal less likely to commit crime. Okay, so we have negative sign. Okay, so we have three explanatory variables which are supposed to explain the number of times arrest. Here, little n is the number of observation. Here, the R square. Okay, R square. How much is the R square? R square is the 0.0413. So what does it mean? What this number means? This regression explained only 4.13% of the variation in number of times arrest. So this is quite low value of the R square. Then how we interpret this estimate regression? Okay, so suppose that the months in prison increased by 12. Okay, suppose that the months in prison increased by 12 months. Then how they will affect the number of times arrest? So you multiply the coefficient, which is the minus 0.034 times 12 months. So you have the minus 0.408. So for a given man, 12 months increase in prison will lead to decrease in arrest by 0.408 for a given man. Okay, so that's how we interpret this one. Now suppose that you add one more variable, and how they will affect your R square of your model. Okay, so we have additional variable in here. This is the average sentence in prior conviction. Basically, when you have the more explanatory variable, the R square increase. But the question is the how much increase. Now in here, R square, here is 0.0422, okay? So R square increased only slightly. Previously, without this variable, the R square was 0.0413. Now R square is 0.0422. So R square increased a little and slightly, even though we have we add one more variable. And we can guess by looking at this coefficient, you can see that you have the positive sign. It means that the positive coefficient means that average sentence increase. Average sentence. Do you think that the average prior sentence increase in number of arrests? And it doesn't make sense. When you have higher average sentence, then we expect a lower number of arrests, but we have the higher number of arrests. It doesn't make sense, okay? And in this case, this variable has limited additional exponential power. First of all, the the positive coefficient doesn't make sense. And also the R square only increase by little, okay? So this additional exponential variable has very limited uh, exponential power because the R square increase by a little, okay? However, that's not the end of story, okay? End of story. Even if the R square is small, we have the less than 10%, less than 10%. Your regression may still provide a good estimate of the what we call the ceteris paribus, that is what we call the partial effect. We talk about the partial effect. Partial effect means that the effect of the variable holding or other factor fixed. Okay, that is the partial effect, or sometimes we say ceteris paribus effect. So even though this your regression perform poor as a whole, you have to look at the individual coefficient and whether this individual coefficient makes sense and also reliable, statistically significant. And how we find out, we will talk about next chapters, whether this individual slope parameter is reliable, which means this significant, statistical significance. If this individual slope parameter estimate is significant, then the regression may provide a good estimate, okay? Because this slope parameter provide a good estimate of the ceteris paribus effect, okay? So even though you have the low R square, don't be so disappointed. Even though as a whole your regression perform poor, you have to look at the individual coefficient. This is not the end of story, okay? And you have to see whether this individual estimate, slope estimate, is a good estimate or not. And that we will talk about chapter 4 next week, okay? All right, now let us talk about some standard assumption for the multiple regression model. Actually, remember we talk about a standard assumption for the simple regression model, and we will have the similar standard assumption for the multiple regression model. Okay, the assumption one, linear. Okay, so this is the same as we had